When we describe solutions that are acids, we describe them based on the magnitude according to which how much hydrogen ion they produce, or protons that they produce in solution. And so a common way of measuring this acidity is with the pH scale. And what pH is a logarithmic measurement of the hydrogen ion concentration. Essentially, your pH scale runs from 0 to 14, and with 7 being exactly in the middle, that would represent a neutral compound, meaning you have your hydrogen ions, your protons, balanced exactly with the hydroxide ions, if we're talking the Arrhenius theory. If we have a pH value that is less than 7, that corresponds to an acidic substance. The lower the number is, the more hydrogen ions that are present. The higher the pH value, the more basic or more alkaline the substance is, and that corresponds to fewer hydrogen ions present. When we take the logarithm of our hydrogen ion concentrations, usually the hydrogen ion is listed in concentration units of molarity, moles per liter, and the hydrogen ion symbol would be written inside brackets. The higher that concentration is, the more acidic the solution is going to be, and thus the lower the pH value would. Now, because our hydrogen ion concentration, the actual molarity of it can vary widely in terms of the magnitude of that value, it's easier to express the acidity in whole numbers, and we're able to take these this wide range of values that ordinarily we'd have to express in scientific notation. If we simply take the logarithm of those values, it turns them into whole numbers, or at least numbers that are on a scale, as I mentioned, 0 to 14, which is much easier for us to handle easily. What you would do is take whatever your concentration is and take the logarithm of that value and then the negative of that number. You should always get a positive value for your pH. So if you had a hydrogen ion concentration or a hydronium ion concentration of 1 times 10 to the negative 7th, you would put that value into your calculator, take the logarithm, and then the negative of that number would come out to a pH of 7. If you notice the relationship between the power of 10 and the pH value, there should always be a close match there. Now here it's exactly the same because our base number was exactly 1. But in general, you should find that your pH value is very close to whatever that power of 10 is. If we had a hydronium ion concentration of 4.2 times 10 to the negative 5th, we would take the negative log of this number, and we're going to expect to have a pH that is close to 5, and we find that our pH value comes out to 4.4. If we have a hydronium ion concentration of 6.27 times 10 to the negative 10th, again we take the logarithm of this value and the negative of that answer, and we expect a value somewhere in the neighborhood of a pH of 9, and we find that our pH value is 9.20. In terms of significant digits with these calculations, go by the sig figs that are in the base number. Now, a more realistic situation is if we have an acidic solution of a given concentration and we are trying to determine what the pH of that would be. So for instance, if we had a 0.25 molar hydrochloric acid solution, the first thing we need to determine is what would the concentration of the hydrogen ion be. We know that hydrochloric acid is a strong acid, so it's going to dissociate completely. And for every hydrochloric acid that dissociates, we get 1 hydrogen ion, so it's a 1-to-1 ratio. And if hydrochloric acid is a strong acid, then all 0.25 molar of it will dissociate, meaning that the concentration of the hydrogen ion would also be 0.25 molar. So by taking the negative log of 0.25, we would come up with a very low pH of 0.60. Notice that pH is a unitless value, so you would not report any units of measure. We can conversely measure the basicity or the alkalinity of a solution by measuring the negative logarithm of the hydroxide ion concentration. And so this is known as POH. It's sort of a lesser used but equally as valid measure of the acidity or the basicity of a solution. Now the thing with pH and POH is that they are complements to one another, and so the sum total of the pH and the POH for the same solution will come out to 14. So if you have the same substance in the solution in the beaker in front of you, and first you measure the pH and then you measure the POH, those two numbers combined should equal 14. If we have a hydroxide ion concentration of 5.28 times 10 to the negative 11th, again we take the negative log, and we would expect to get a POH value that is close to that power of 10. Alright, and so here we get 10.3. Now remember that the pH scale with values less than 7 equals an acid, greater than 7 equals a base. Now that's going to be reversed if you're talking POH. To get the pH of the solution, you would need to subtract this value, 10.3, from 14 to get the more standard pH that you would compare with that scale. So a POH of 10.3 would actually be representative of an acidic solution, because your difference would be 3.7. Again, take a more realistic example. If we had 0.0010 molar magnesium hydroxide solution, when magnesium hydroxide dissociates being a strong base, for every one magnesium hydroxide you actually get 2 hydroxide ions. So when we take the concentration to take the logarithm of it, we're actually going to be using 0.0020 molar. Again, because it's a 1:2 ratio, magnesium hydroxide to straight hydroxide ions. Taking the negative logarithm of that value, we should get a POH of 2.7. Subtracting that from 14 gives us a pH of 11.3, and therefore we would classify this solution as we would expect to be basic.